So we left off last time with the three-phase problems. I think we had this problem statement, and we spent some time going from the problem statement. If I read through this real quick, a three-phase positive sequence, so that's ABC, positive phase sequence, Y-connected generator with a generator impedance. The internal phase voltage is 120 volts, so that's that the source is. The generator feeds a balanced Y-connected load, so it's a YY. Having an impedance of 39 plus J28 ohms per phase. One of the big things when you see a three-phase question that you probably want to ask yourself, is this total resistance for all three phases, or is it resistance per phase? So if you see a test or homework question or something, if it doesn't say ohms per phase, you probably want to investigate that. The impedance of the line connecting the generator to the load is given. We take the A phase internal voltage of the generator as the reference phase. That basically just says take the A phase as your reference 0. And we'll get this set up and do a variety of calculations. And I think we did that as we were finishing up last time. But I wanted to reiterate, most of these problems are in a verbiage form like this, and you got to really read it for all its meaning. Positive phase sequence, this reference business. And when you go through this, you should probably build a single-phase equivalent circuit. Granted, we have a YY, and we don't want to forget that it's a YY. But there's no sense in making all three phases. We'll just make the A phase. And you could do the B phase or C phase if you wanted to, but it's usually easier to do the A phase. And then we can just add and subtract 120 degrees on our answers. Yes? Delta generators. Well, I think you got a homework problem like that on delta generators. We're definitely going to do a delta load in the next example. Yeah. So we're not going to leave the delta behind. Other questions? Okay, so I put the generator impedance here. I put the line impedance here, and then I put the load impedance. Again, we usually use capital letters indicating the load. So I've got capital A and capital N. We have lowercase letters indicating the generator. I've got the A phase at 0. Remember, unless told otherwise, it's always VRMS. So even if I would have just written this with V, we would have assumed RMS. Everything in three phases RMS unless noted otherwise. I think we calculated the current in this last time, but I'll go through it. We could talk about this current here. We could say that's I little a big A, and that's a phasor current. And that's really just as easy. I mean, this is a very simple circuit, right? Some of you in lab yesterday recognized that there's very little current in that neutral line, right? The rest of you will hopefully recognize that tomorrow. Remember, speaking of that, we're split in the lab section. Some of you are coming at, 8:30, some at 9:30, is that right? So make sure you show up at the right time. The Tuesday group, did that work out okay? Okay, good. Okay, hopefully that was worthwhile so you could get a little better experience in there. So let's do that current. We can say that the current is the voltage divided by the total impedance. So we're going to have 120 at 0 divided by, if I take 0.2 plus 0.8 plus 39, I have 40. Plus J 0.5 and 1.5 and 28 is going to be plus J, 30? Okay, because that's your Z total. And if you run the math on that, you end up with 2.4 at an angle of minus 36.87. That'll be amps or amps RMS. So that was AA. If we wanted AB, what would we get? I mean, not AB, I'm sorry, BB. So I could continue on and say, and I little b, big B, should have the same magnitude, right? 2.4. And then what's our angle going to be? We're a positive phase sequence, positive A, B, C. So that means for the B, we'd do what? Yeah, subtract 120, so I get minus 156.87, because we subtracted 120, amps, RMS. And likewise for I, little c, big C, I've got the same magnitude, 2.4, because it's balanced, and then I'm going to add 120. I add 120 to minus 36.87, and come up with 83.13 amps RMS. And I'll do this probably a couple more times going through the B and C phases, and then I'm figuring that you can take this information and add and subtract 120 in the appropriate place and won't keep beating that. Yeah, this is little a, big A, so that's the current through here. Yep. Other questions? Well, let's say that we wanted to find the phase voltage at the load. Okay? And like I said, circuit simplification, circuit analysis is not the tough part of this, it's the definition. So sometimes I will take a minute and I'll write something out. It'd be a lot easier to say what this was in variable form, but we have to be able to go from the verbiage to what variable are we talking about. What is the phase voltage at the load? Well, it's probably V, right? It'd be a good way to stall on this, V. And then the subscripts. What's the phase voltage at the load? Well, we know phase voltage is from line to neutral, right? Okay, so it's probably going to be that. What would we call that? AN. Voltage at A, capital A, across the load with respect to capital N. Voltage AN. Right there. Okay, so that's what we're looking for. What's a good way of getting that? Now, you could do voltage division, all kinds of things, but since we know this current through here, we could just take the current and multiply it by the impedance. So we'll take I little a big A, and we will multiply that times 39 plus J 28, which should give us 115.2 at an angle of minus 1.19 degrees. That's volts RMS. Okay. And then if you wanted A or BN or CN, subtract 120 or add 120, right? Same magnitude, different angle. Well, what if we ask for the line voltage? At the load. Okay? The line voltage at the load. What's that? Well, line voltage is really line to line, isn't it? So what would be an example of line to line? AB would be AB. You could say BC. You could say CA if you wanted to. I'll do AB. That's as good as any of them. So how do I get there? Well, let's see. I could start with this one, right? I could use that one, and I know that I have to take V for the phase, the magnitude of that, and I multiply it by the square root of 3, and what am I going to do for the angle on this thing? Let's see, this is positive phase sequence, so I do what? I add 30 degrees, don't I? If we go back to our pedestrian's guide for three-phase that we came up with last time, multiply by root 3 and add 30 degrees because it's positive phase sequence. If it was negative phase sequence, I'd subtract 30 degrees. So with that, I take this 115.2, I multiply by the square root of 3, and I have then an angle of, let's see, minus 1.19 plus 30 degrees, and that turns out to be equal to 199.58. We'd probably just call that 200. 199.58 at an angle of 28.81 degrees, and that's volts RMS. Uh-huh.
So when we find phase voltage as a load, is our load the 39? Is the impedance of the load 39 plus J?
Yes, this is the load. This is going to be Z for the load. Whereas this is Z for the line. And this is the internal for the generator. Did that work out math-wise? Did we get that right? I'm going to check a couple of those. Yeah, I think we're good. Okay. Oh, what about the phase voltage at the source? And obviously, if someone wanted the set of these, we'd need to give them all three voltages, add or subtract 120 degrees. I won't belabor that. But let's move on to the phase voltage at the source. What's that going to be? Well, remember that phase voltage is the line to neutral voltage. So if I were to draw a picture of this, there's the phase voltage at the source. Now, you might think this is a trick question. Is it 120 at 0? No, that's the internal voltage. In an ideal world, if we didn't have this impedance, if we didn't have losses in that generator, the answer would be 120 at 0. Okay? If this had no load on it, the answer would be 120 at 0, because if this current here was 0, what would be the drop across that generator impedance? It would be 0, wouldn't it? But since we have a load on it, we're expecting a current. In fact, we found IA to be a non-zero number. We would expect to have some voltage drop across this impedance here, and this voltage at A with respect to N should be something less than 120 at 0, right? So we're looking for voltage A, N, voltage A with respect to N. Let's see, what's a good way of doing that? Yeah, we can just use just good old-fashioned analysis. 120 at 0, and then we'll subtract off the current, which is 2.4 at an angle of minus 36.87, times what? The impedance, 0.2 plus J, 0.5. Let's see what we come up with there. So, has anyone come up with 118.9 at an angle of minus 0.32 degrees? Okay. So, the work here is not necessarily in the calculation of the simplification. The work is oftentimes in trying to figure out what's meant by the verbiage here. So again, just like with our work in power, so much of it is trying to interpret the problem. Could we get the line-to-line voltage at the source? Yeah, we multiply this by the square root of 3 and add 30 degrees to that. I won't necessarily go through that, but you could do that if you wanted to. Yes?
So earlier we were finding the current of the light big little c, big B,
Hmm.
little c, big C.
Mm-hmm.
That was just by inspection of the main host, right?
Uh-huh.
Because we don't have it up there. You said if there were, those would be the current.
Right. I mean, if we drew the full circuit, then those would be the currents. Yeah.
But there's no line B and C.
Yeah, then I didn't draw the picture. I didn't take the time to draw the full picture with all three phases. I mean, when I have the currents here with this answer, and with this answer, that's actually an answer to giving the set of the line currents. Okay. That'd be the full set of all three. Well, let's move on then and tackle the next little twist here. Which is it says the Y-connected source above, that was the last problem that we did, feeds a delta-connected load through a distribution line having an impedance, and the load is given an impedance. So let me draw this in very schematical form here. So I can leave that up there. So we have the Y that we had before is feeding a delta. Okay, and each one of the deltas, Z sub delta, is given as what? 118.5 plus J 85.8. And the line connecting them the impedance of the line connecting them, we're told, is 0.3 plus J 0.9. So we have a classic Y delta problem. And if I have a Y delta, how would I like to analyze it? I would like to convert this to a Y. That's going to make my life a whole lot easier. So one of the ways that I'm going to do it is I'm going to say that this Z delta can be converted into a Y, so I could say that ZY for the load is equal to, what do we say about how delta relate to Y? Remember we had the expression that ZY is equal to Z delta divided by 3. That was our general expression that we had last time. So I'll take this Z delta and divide it by 3. So when I do that, I'm going to take 118.5 plus J 85.8, divide that by 3, and that gives me then 39.5 plus J 28.6, and that would be ohms per phase. So I can make the single-phase equivalent circuit with this. The single-phase equivalent circuit would look very much like the source of the last one that we had. So we'd have a source here with 120 at 0. It's also positive because that's the same as the last one. Then it has some generator impedance, which is the same because we're using exactly the same source. What was that generator impedance? 0.2 plus J 0.5. And then things get new. We've got a new line impedance. What was that? 0.3 plus J 0.9. And then we get the load. And we'll put the load over here, which is 39.5 plus J 28.6. And maybe we should say that this is our Y model. for the real delta. We want to keep that in mind. We are modeling a delta. We're trying to make our life easier by modeling this delta as a y. I already took the delta, I divided it by 3, and that's what the model is. Okay. Questions with that? Yes?
I guess in the handout it says the load
Uh-huh. Mm-hmm.
I would kind of think that is each. I guess that's not perfect.
Perfect.
You divide by 10.
Okay. Let me grab a piece of paper here. So we've got that this delta. So we had these line impedances here going into our delta. So we'll have something like this, right? And each one of these is 0.3 plus j 0.9, right? Right there, and right there. We're good with that? And then each one, because this is 118.5 plus j 85.8, that's ohms per phase. So I know that each one of these, this, and that, those are all 118.5 plus j 85.8. And what I'm trying to do is by dividing that by 3, then I convert this into a y.
That only works with typical.
Only work, what do you mean by typical?
Like all of those are the same. So that's these on the delta.
That'd be balanced, yeah. The answer is yes. It's got to be balanced. So I'm trying to convert this whole thing to something that looks like that, where each one of these are still the 0.3 plus j 0.9, and then each one of these are 118.5 over 3 plus j 85.8 divided by 3. So my dividing by 3 had nothing to do with the 3 phases. My dividing by 3 had to do with the conversion from delta to y. Okay, that's an important point. I'm glad you asked that. Everyone's good there? So now what we've done is I've taken this and I've hooked it back up to my source. We okay with that? Okay. So let's see where we are here. This must be page 3, and we're on to 4. So this is the circuit. I think I got enough room here. I'll stay on this page a little bit longer, and let me see if I can calculate this current. I'm going to call this I little a big A. So what's that going to be? Well, it's the voltage, 120 at 0, right? Divided by the total impedance, what do we have? 0.2 plus 0.3, 39.5, that gives me 40 plus j 0.5 and 0.9 and 28.6. That gives me 30, doesn't it? Yeah. So what do I come up with? 2.4 at minus 36.87 amps RMS. Really the same thing as last time, didn't we? I mean, I just copied this out of the textbook. Keeps the numbers easy. So that's what they went with. Now, we'll start asking some kind of difficult questions here. Maybe I'll work my way backwards up this page here so that we can see the circuit. Let me ask the question, what is the phase voltage, or the phase current in the load. Okay? I'd like to find the phase current in the load. What is that? Well, some people might think that this is I little a big A. This is a trick question, isn't it? This is really just 2.4 at minus 36.87. I mean, that's the current through there. That's the current through the load, isn't it? Yeah, but this is what? This is a model. What does our real load look like? It's the delta, isn't it? So what I need to find, so this is for the model. I got to find it for the delta. So what I really am going to have to find is, let's say I little a, not I little a, IAB. So IAB. Okay. So how do I get that? Well, it should be equal to I little a big A divided by the square root of 3. Is that right? And then what do I do to the angle? Minus 30 degrees, because it's positive phase sequence. So in going through that, that turns out to be equal to, if you take the 2.4 and you divide by the square root of 3, you should get 1.39. At an angle of, if you subtract 30 degrees from that, you get minus 6.87 amps RMS. Let me check that, double check that magnitude. Oh yeah, maybe I don't subtract 30. Let me see if I'm going to, let's see, I think I got to add 30. What did I say last time? If it was positive phase sequence from last time, didn't I have the example that I little a big A was equal to the square root of 3 times I phi, and with positive, subtract 30. Okay. But we're looking for this guy here, aren't we? So, yeah, the example that I just did a few minutes ago, we used voltage, and voltage is different than current. Yeah, okay. So this is from the last lecture. Okay. Didn't I have an example that was something like this in the last lecture? Okay. So, yeah, that was our guide to three-phase. So the guide to three-phase. So if I want to solve for I phi, what's that going to be? I phi is going to be, I'm going to have to take the I little a big A, divide by the square root of 3, and then to get that over there, I've got to add 30 degrees, don't I?
Do you verify that negative 2.7 is correct?
Yeah, so this should be a positive 30 degrees.
So then does that change the rule? It's a bit false.
No, I think the rule is still very valid. The rule, because I'm not looking for this. This is what I'm given.
Oh, yeah.
So then I have to move that to the other side. I mean, this positive came because this minus 30 was moved to the other side. Okay. I mean, if you want to see the math behind it, I've got what I little a big A then I'm going to divide that by the square root of 3 at minus 30 is equal to I phi. So that turns out to be equal to the magnitude at over square root of 3 at an angle of, I can move that up by saying it's positive 30. So that's where I came up with that. So I should have had that as positive 30 to begin with. So the rule's okay, it's just that it needs to be rearranged for our use. So that would be IAB, which is the phase current in the load. So we have to always remember that our load, the real load, is a delta. And we're not necessarily looking for this current here. We're looking for the current inside that delta. So we're looking for that current possibly, which is the phase current, not the line current. Yes? I'm sorry, I don't understand your question. No, it's from adding 30, because I'm starting out with minus 36.87. Isn't that what we had here? Yeah, minus 36.87. So if I add 30 to that, I get the minus 6.87. So what if we ask the question, what is the, let's see, what's the phase voltage? Phase voltage at the load. So where's that going to be? Well, normally we think of the phase voltage as line to neutral, but in this delta, isn't that the phase voltage? So we're really going to have to calculate what? VAB? Because if we wanted it to load. So we could get VAN. If I go back to this diagram with the model, VAN is fairly easy, right? So I could say that VAN is equal to the current, IAB or AA, times 39.5 plus J 28.6. So this, what does that current? That's 2.4. We're not done yet. 2.4 at minus 36.87. So what's that turn out to be here? 117.04 at minus 0.96 volts RMS. But that's really not what we want. We don't want AN, we want BN. This is what we want. So how do I get that? I mean AB, not BN, AB. Well, what do we have with the guide to three-phase? What did we say VAB was? Root 3 V phi plus 30. Okay, so how do I get there? I'm going to take 117.04 and I'm going to multiply it by the square root of 3, and then I'm going to have minus 0.96 plus 30 degrees, which gets me, what, about 202? 202.7 at an angle of 29.04, yeah. Volts RMS. So that's what AB is right there. Questions with that? So let's go backwards on that. I get just enough time to finish this up. If we started and we said that VAB was equal to 202.7 at an angle of 29.04, and I wanted to get voltage AN, what would we do? Well, we know from our work last time, right there, that voltage AB is equal to the square root of 3 times V phi at plus 30. That's for positive. Well, we got all this stuff here. So if I wanted to solve this for V phi, what's V phi going to be? VAB, or the square root of 3 at an angle of what? Minus 30, because I'm moving it to the other side, right? Okay, so that's our new expression. So therefore voltage AN is going to be equal to AB, 202.7 divided by the square root of 3 at an angle of 29.04. Did I do this right? Minus 30. So I got the negative there. So 202.7. $117.0 at an angle of minus 0.96. Is that what we started with? Yeah. So when I gave you these expressions last time, you had to be careful which way you were going with them. If you were going one way, you subtract 30. If you were going the other way, you add 30. Questions of that?
Did your calculation just give you the whole number of 117?
Let's see. Oh, when I divided 202.7?
Yeah. I'm just curious if that 0.04 showed up in that calculation.
Well, originally we had 202.6.
I got 117.0289, but I think like he is saying the 202.7 probably isn't quite right.
I know it's a really small value.
Yeah, I was just rounding off. Well, what we'll do when we get together next time is we're going to go back and we're going to look at this thing and start to talk about the power. So we'll come up with some equations for power, but power is also pretty easy to calculate because we can go back to our old friends of just squaring the current and multiplying it by the resistance. Do the same thing for the reactive, except we'll have the impedance in there. So that's what we'll do next time.